Hi, my name is Adam Ost, and this is a presentation for the 2020 Virtual Society for Mathematical Psychology Conference. I'm going to be talking about integrating word form representations with global similarity computation and recognition memory. So the way we think memory basically works is that memory is determined by the similarity between the retrieval cues and whatever was learned in the learning episode. This is basically how all models of memory work. In the case of recognition memory, if we had a study list like cat, cheese, truck, and queens, and we were to have a test word like kitten, the way we think this operates is that there's a global similarity computation. There's a match between kitten and each of these words that is aggregated in some way, such as calculating a sum or an average. But there's still some questions here. What is similarity? And this question becomes especially pronounced by the fact that there's similarity on different underlying dimensions. So for instance, there's semantic similarities, such as, cat is similar to kitten in terms of their semantic features, but there's also perceptual similarity, even among the words themselves. So for instance, both letter strings have T in the third position. Now, how do we actually assess these forms of similarity? Well, to do so, we need representations. And now semantic representations, there's been some progress on because these have often come from semantic space models, such as latent semantic analysis and word2vec, where words are learned on the basis of their co-occurrence with other words in the natural text, usually with a large corpus. And there's been some progress in using these in memory models, such as free recall models and recognition memory models have used these representations. And an advantage is that you can basically plug in these representations and derive similarity effects and false memory effects for free. It just kind of falls naturally as a consequence from the fact that you have well-specified representations and a well-specified retrieval model. Now, orthographic representations, on the contrary, there hasn't been as much work on. And this is surprising because there's actually representations that have been available. There are word form representations that have been developed in psycholinguistic models of reading to make predictions about naming and priming latencies. These representations fall into two camps, including absolute position models, where words are similar to the extent to which letters occupy the same absolute positions, and relative position models, where words are similar to the extent to which letters are adjacent to the same letters. I'm going to be going through each of these kinds of representations. And the gist of the talk is going to be about, what consequences does this have if you calculate global similarity on the basis of these representations in recognition memory. And I'm going to be coming back to the semantic similarity question as well. But first, let's say you want to calculate the similarity between the strings perk and person. Well, a simple way you can do this is you can just count up the number of in-position letter matches and then divide them by the alignment length. This is the basis of the slot code representation, where it's almost as if you can picture each letter falling into a slot, and then you just compare the slots vertically. And if there are matches, then that counts it up. And but they have to match in the exact position relative to the start of the word. This has been used for a while in models like the interactive activation model of McClelland and Rumelhart, and also Max Colhart's model. It's relatively easy to specify in a connectionist framework. With that being said, there have been some problems with this model that have been identified over the years. Many problems, but one that I'd like to highlight here is the fact that you can't really align suffixes very well. So for instance, these two words, vacation and representation, have a common suffix, which is the tion, but they are not aligned relative to the start of the word. And so therefore, the similarity is relatively low. But if we align these words relative to the end of the word, then now we're able to pick up on some similarity between these two strings. This is the basis of both edges representation, where you essentially calculate letters similarity as distance from both the beginning and the end of the words. And what I've done in the modeling, the memory modeling I've done, is I've also introduced a weighting parameter that weights the contribution of the start-based and end-based similarities, with the idea being that a priori we might expect the start-based similarity to have a larger influence. Now, a more sophisticated positional model is the overlap model of Gomez, Ratcliffe, and Perea. Now, what this does is it's similar to the slot code model, but it relaxes the assumption that letters are only represented in the exact position in which they occurred. Instead, letters are represented in many different positions, and this is determined by a standard deviation parameter of a normal distribution. So for instance, if we look at this letter A here, it has the strongest association with the third position, but it also has a weaker association with the second and fourth position. And so that can be used, that can be leveraged in calculating similarity. If this standard deviation parameter gets sufficiently low, then it actually defaults to a slot code type model. And you can see here for the first letter, that is what you see, where it only is represented in the first position. Now, a problem with all absolute position schemes, the overlap model has less of a problem with this, is aligning substrings of words that don't respect position. So in remembering and members, there's a common substring here, but they are shifted by some letters. And this is a problem for both slot codes and even for n-based schemes. If we have remembering and members, we can't align these to either the start or end of the word. Now, this is the basis of relative position models, where we can think about instead what letters accompany other letters in the words. This is most commonly represented in terms of bigrams. So instead of thinking of, now what we can do is we can think of similarity as just what common bigrams occurred across these two strings, such as ME and EM, and not care about which position they occurred in. And this is common in models like Serial and the OB1 reader. When comparing these strings now, I want to point out that in the bigram model, it's common to also represent the start of the word and the end of the word. And so then you have this combination as essentially as a bigram. And we can essentially count up these common bigrams across the two words, divide by the alignment length, and now we have a similarity between these two strings. So now we have a number of representations that have been developed. Now, what does this have to do with recognition memory? Well, going back to our early example, now what I can do for a number of recognition memory data sets is I can compute the similarity between the test word and each word in memory. And I can do this for each of the representations we have. And before I make contact with data, what I'm actually going to do is I'm going to raise these similarities to a power, P, which is a free parameter. And then after the fact, I'm going to average all of these similarities together after this transformation to produce an index of global similarity for the test word. Now, the reason why I have this power parameter in the model is that it's similar to the C parameter in GCM, which is as this power gets increased, it selectively punishes low similarity items, such that high similarity items essentially dominate the global similarity transformation. You can see, for instance, when the power is as high as 5, word similarities as high as 0.4 are all pushed down to 0. So you have to really have a high similarity value to even enter the global similarity computation. And then what I did was I made contact with data using the LBA model. So this links global similarity to both response time and accuracy. And what these representations give us is a way of calculating drift rates for individual probe words. And so what I have here is a capital V parameter, which is essentially a drift rate intercept. So this can be used to vary across conditions, and such that we can capture differences in performance that don't have anything to do with orthographic similarity. At the same time, we have an alpha parameter associated with this global similarity, with the idea being that if this scale parameter goes down to 0, then global similarity exerts no influence on performance. Now, each of the representations were fit separately as hierarchical LBA models with DEM-CMC. The models were compared with DIC as model selection. And the data sets that were employed all used lists of unrelated words. So there's no a priori similarity structure. And the reason why I made this decision is because then you actually have a range of different word types present. You have some words that are highly similar in the set, and you have some words that are don't have high similarity, and you have some words that are just moderately similar. So there's lots of different kind of similarity types that constrain the underlying fit. Now here are the results of the model selection here. And so these are DIC difference scores relative to the winning model. And in 3 of the 4 data sets, bigram representations win. So these, there's one data set of my own where both edges representation scheme wins. But I'd like to point out here that with the bigram scheme, there's one data set here, the Cortese et al. Data set, that it has a very large advantage on. This was actually because it was a very large data set of about 150 subjects with close to 2,000 trials. It was actually a challenging data set to fit. Now, how well does the model do any of these models actually fit the data? Well, what I did here is I independently defined different types of lures using Levenshtein distance. High similarity lures are lures where one word from the study list has a Levenshtein distance of 1 to the probe word. So for instance, if you had cat versus cats, that'd be a Levenshtein distance of 1. In addition, I had moderate similarity lures where at least one word had a Levenshtein distance of 2 to the probe word. So for instance, cheese versus chose is a Levenshtein distance of 2. There were also low similarity lures with a distance of 3. So chaotic versus meiotic would be an example of that. And very low similarity, which is a distance of 4 or higher, where these are getting closer to just completely unrelated orthographically. And here are the results of the model fit. This is the fit to the Cortese et al. Data set. The model is in red and the data is in black. We have false alarm rates on the left and response times on the mean response time on the right. And what I'd like to point out, first of all, is that the effects of orthographic similarity are particularly large. In this data set and in several others as well, the difference in between the lowest similarity values and the highest was as high as 0.20, which is about as big of an effect as you can actually find in a recognition memory data set. So it's a fairly pronounced effect. Now, there were also much smaller differences between moderate and low similarity lures. Now, this is actually a direct consequence of the nonlinearity parameter I introduced to the model. Which is quite common again in models like the generalized context model, where similar results have been found in short-term recognition. Now we have some orthographic representations, but how do these compare with semantic representations? Now I mentioned earlier that most models have focused on semantics. Does that imply that semantic representations are more important? Well, to get at this question, what I did here was I also included semantic similarity values in some subsequent fitting. I introduced a separate power parameter here, PS, because it seemed to perform better. And in addition, a weighting parameter, W, which weights the contribution of orthographic similarity in determining similarity. So if W approaches 1, then only orthographic similarity influences the global similarity computation. Semantic similarity doesn't do anything. Here's the result of the weighting parameter across each of the data sets. And what surprised me a lot is that 3 of the data sets showed quite high values of this weighting parameter that suggested a dominance of orthographic similarity. There's one data set, the Cortese et al. Data set, that leaned a little more towards semantic, but only slightly. It still was hovering around 0.5, which surprised me quite a bit. This suggests that orthographic representations, are pretty consequential. So just to summarize, bigram representations generally do the best job at capturing perceptual similarity. And a take-home message for memory models is that you can actually represent bindings between letters in the same manner as bindings between words in associative memory tasks. So essentially, direct associations between the two. So in memory models such as Totem or Minerva, we represent pairs of words in the same way. We don't represent them in terms of position, we represent them in terms of direct associations. Perceptual similarity effects are also big. There's very large differences in false alarm rate between low and high similarity items, even though these are lists of completely unrelated words. And models are able to capture this with these types of representations. And then finally, perceptual similarity seems to contribute at least as much as semantic similarity in predicting recognition memory performance, which suggests that maybe we should be taking these orthographic representations a little bit more seriously when we are building our memory models. Thank you.